In this video, we're going to take a look at conservation of energy as applied to the loop. So we'll play this video and just take a look. So special track is made in a vertical loop. To see what it takes to execute a loop without the car falling. This is an example of just making it over the top, which is a really common topic in circular motion, especially in the vertical plane. A couple of things that are interesting to me about this video is that when we take a look at the kind of car that was used, it's a very small car, like a Super Mini. And the speed of the car going into the loop is not actually that fast. And we also know that the car is going to slow down. So the reason why it's not a super powerful vehicle, or because we're just counting on conservation of energy to make it over the top. And the speed at the top is going to be actually much slower than the speed at the bottom. So we'll take a look at that. Some of the details include the height, 40 feet. And of course, this condition to just make it. So this is coming to us from circular motion, and we know at the top that the centripetal acceleration is downward. And as far as forces go, we have the normal force pulling upward, and we have gravity pulling downward. So the condition to just make it says that, well, when we take a look at all the forces that are acting on an object, and of course on the left-hand side, we include what the forces are. So that's the normal force pulling upward or pushing upward, and then gravity pulling down. And then the acceleration for moving the circle is v squared over r, but the acceleration is downward, so negative m v squared over r. So to just make it, that means that gravity is enough to keep the motion in the circle, or we're weightless. So the normal force would be equal to 0. And so the condition for just making it over the top of the normal force is 0, then the masses cancel on both sides, the minus signs cancel on both sides. Then our condition to just make it is that v squared has to equal g over r. And that's also our zero gravity, or our weightless condition. So what happens if you go slower than this? Well, if the car goes slower than this, it falls. Then gravity is too much. So sometimes, well, what's the force that keeps it on the track? And there is no force that keeps it on the track. It's just that gravity is busy executing circular motion, and there's not enough gravity to separate it from the track. And if you're going faster than this condition, then you actually experience what we would call negative G's, because our driver is going to be inverted and it's going to be pressed, or feel pressed against the outside. Okay, well, that is our condition for just making it. And that's the condition at the top. So I'm going to include the subscript top here. Now let's invoke conservation of energy. So on the way in, we have kinetic energy. So the total energy is going to be equal to 1/2 mv in squared. And then that's also going to be equal to 1/2 mv top squared plus the potential energy at this height, which is mass times gravity times height. But the height is twice the radius. So I'm going to write 2r here. Now, if v squared at the top has to be equal, actually, this is G times R. Yeah. If V squared at the top is G times R, then I can make a substitution. So 1/2 V n squared is equal to 1/2 G times R. And now you can see there's some really interesting results that happen from this. So these are like terms, actually, because they're both in terms of m, g, and r. And the 1/2s can cancel as well. So if the easiest way to do that is to run this through and just multiply everything by 2. And then, of course, the m's cancel out. So we'll do that at the same time. So m's gone, gone, gone. And multiplying through by 2, then we have v n squared is equal to g times r plus 4gr equals 5gr. Now, if we plug in the numbers for this, we want to see what that's equal to, where r is equal to 6.1 meters, then I can go ahead and just calculate that. So 5 times 9.8 times 6.1, and then take the square root of the answer. And so Vn is equal to 17.3 meters per second, which if I wanted to do in miles per hour, I would multiply by 3,600 seconds in an hour and then divide by 1609 meters in a mile. And I get just 37 miles an hour, that's it. And V at the top, and this slows down not because of braking, but just because of gravity, is G times R, the square root. That's just 7.7 meters per second, which translates to 17 miles an hour. And there's lots of different ways that you can do this, because we could also just do this from sort of a roller coaster point of view. So I'll make the loop a little bit smaller. And in a roller coaster, all the kinetic energy comes from having a certain height that we're starting from. So I'm going to call this capital H and ask ourselves, how high does this have to be in order for us to make it over the circle? So in that case, instead of starting off with kinetic energy, the total energy would start off as potential, mg, and I'm going to write capital H here. And then the same thing is true. So by the time we do, we're going to have mv squared top, mg times 2r, and add these together. Well, this is going to be equal to 2.5. So 1/2 plus 2 is 2.5 mgr. And then a super interesting situation happens because the mass cancels, but also G cancels. So it doesn't even matter what planet you're on. And sorry, this is supposed to be an R here, not the height. And so H, in order to make it over the top, needs to be 2.5 times greater than the radius. And of course, this is twice the radius already, right? So this is actually quite exaggerated. So this is already 2R. 2.5R is only going to be about that high.